number 32. And I'm going to be speaking about what are some different driver topologies for ultrasonic transducers. And specifically today I'm going to be covering op amps. This is more of a general overview rather than a really specific deep dive in understanding their experimental use. But let's start going over the general topology of implementing driving circuits for ultrasonic transducers. So there are a couple of different topologies, and I'm just going to broadly group them into three categories. The first is the power op amp. The next is the bridge topology, and the final one that I'm going to describe is the oscillator. Now these two I'll describe in coming videos, but the power op amp is what I'm going to be focusing on for this one. So, but before we get into the power op amp topology, or just basically a description of the pluses and minuses of that system, let's just talk about how piezoelectric transducers, how their drivers are set up in general. So first we have an AC, well generally we have an AC power supply, which is how you get energy into your system. Well, you got to plug into the wall, or you have to get that power in some way or fashion. The next conversion that happens is from AC to DC, and that's going to be how you are going to supply voltage to your driving circuit. So that's really not a that's kind of a trivial thing to talk about here, and not really specific from getting from AC to DC rectification. A bunch of different ways to get from AC to DC there. Finally, well, not finally, actually, for the real meat, we have the driving circuit itself. So we have either that op amp circuit, we have our amplifier, which can also be a bridge driver, which is naturally going to be a square wave type of drive, and also an oscillator, which in some cases doesn't require any external input, basically any digital input for what the frequency is going to be. So after that driving circuit comes an important part, and that is the impedance matching circuit. Now the drive circuit of your is going to be optimized and just naturally want to be able to efficiently drive a certain current and a certain voltage to make best use of its characteristics. However, your transducer will be different than your driving circuit, especially if you're using off-the-shelf components versus really going in and designing, let's say, a Class A amplifier versus pulling a chip off of the shelf and then needing that to be adjusted in terms of, let's say, current and voltage to your specific device. So an impedance matching circuit is needed in that case, and that could be a combination of things, but the simple fact and idea of it is going to be a transformer. If you need more voltage or smaller voltage in order to transform that voltage and current into what can best drive energy or power into your transducer. If it's a higher impedance transducer, well, you're going to need higher voltage. If it's a lower impedance transducer, usually drive circuits are naturally going to be apt and just naturally suited for high current, low voltage. That's many of the chips you'll find. However, if you do have a higher voltage scenario, or I mean, you want to drive a lower impedance load than what's rated or what comes most efficient for your specific topology, then you'll need to have a transformation of voltage downward in a step down configuration. Another way that we do impedance matching is using an LCR, an LC circuit for impedance matching. You can look more on that. I won't be necessarily covering the details there, but you can also form resonance circuits. You can use series and parallel passive circuit components to amplify voltage and current, but not power, because your power is going to remain constant. But if you drop the load of your final device, you're going to end up increasing the power, but not increasing what you can get out theoretically maximum from your amplifier. And then finally, you have your beloved transducer that's going to be receiving all of that love, that high voltage love. So let's take a look here. Let's take a look at the power op amp and some of the benefits and just some of the attributes of it. So the power op amps are usually lower frequency, less than 1 megahertz typically. If you want to usually go higher than that frequency, you're either going to have to look at a different topology such as the oscillator or half bridge driver, or you may have to design your own amplifier using certain components such as a BJT or a MOSFET to actually implement your amplifier kind of from bare bones components versus buying an amplifier off the shelf from which you can which is typically represented as the op amp, as the amplifier. The other part of it, the nice part of this circuit, the power op amp, which isn't a given actually in all cases, as I'll describe, is that you have a sine wave in and you get a sine wave out. So you have good spectral purity of your final signal, and you also have very good control over amplitude. So reducing the input amplitude also reduces the output amplitude. So you have you'll be able to have pretty good control over that. In the next case, so I mentioned easy amplitude control. Also, you can use a dual or bipolar power supply, meaning that you can either have positive and negative voltage supplied to your op amp. Therefore, you'll be able to swing your output voltage both positive and negative, or you can only supply a positive voltage and perhaps and ground the other terminal or power supply end of your op amp. And then you'd obviously wouldn't have that full voltage range, that swing, but through a capacitor, if you drive your transducer through a capacitor or your impedance matching circuit, including a transformer perhaps through a capacitor, then you'll be able to still get AC current and AC voltage at the other end, which has a bipolar nature. Finally here, we have audio devices. Yes, for let's say below 100 kilohertz, especially below 40 kilohertz, in that range, you'll have a lot of audio components, audio op amps that will audio amplifiers that will work for your application. So this is kind of unique. There's a lot of components available, and you don't necessarily have to cook up something. You can do a little bit of searching and find components that are very widely available. They're not perhaps most used for ultrasonic applications, but they can be applied for those purposes. Perhaps it's not their main use case, but they will actually work for driving your ultrasonic transducers. So check out power op amps for audio applications. You'll definitely get your 20 kilohertz transducers running on that. Probably 40 kilohertz as well. Maybe with a little bit of bandwidth hit there, but you can still put a decent amount of power. You couple that to a transformer and you're rolling. Usually audio amplifiers are intended to drive 8 ohm or 4 ohm loads with high current, so you'll definitely need a transformer because that's typically not the voltage current space we're driving our ultrasonic transducers in, but for a 40 watt drive, you'll definitely find some decent components out there in the audio kind of realm. So you've been watching The Shock Show with your host, Dr. Shikani. This has been episode number 32. We're going to be continuing on the next couple of episodes, talking more about the bridge driver and also the oscillator circuit and their advantages and disadvantages. So stay tuned. I look forward to seeing you in the next video.